the hidden science of the PN junction, the heart of modern electronics. What if I told you that almost every electronic device you use, your phone, your laptop, even solar panels, relies on a tiny, invisible boundary? A boundary so powerful that it controls the flow of electricity itself. This is the PN junction, the unsung hero of modern physics and technology. But how does it actually work? And why does a simple combination of two materials, P-type and N-type semiconductors, create the foundation of all electronics? Let's break it down. The building blocks, P-type and N-type semiconductors. To understand the PN junction, we need to meet its two key players, P-type and N-type semiconductors. At the atomic level, semiconductors like silicon are special. They don't fully conduct electricity like metals, but they aren't insulators either. We can manipulate them by adding impurities, a process called doping. P-type semiconductors are doped with elements like boron, creating holes, missing electrons that act like positive charge carriers. N-type semiconductors, on the other hand, are doped with phosphorus, introducing extra electrons that move freely. Forming the PN junction, a barrier is born. Now, here's where things get interesting. When we join a P-type and an N-type semiconductor together, electrons from the N side rush to fill the holes in the P side. This creates a region in between, the depletion zone. The depletion zone is different. It has no free-moving electrons or holes. It's an electric barrier. This region stops more electrons from flowing unless we give them an external push. The magic of biasing, turning the switch on and off. But how do we make this PN junction work for us? By applying a voltage, a process called biasing. If we connect the positive terminal to the P side and the negative terminal to the N side, the depletion zone shrinks, allowing current to flow. This is called forward bias. The circuit is on, but flip the voltage, connect negative to P and positive to N, and the depletion zone grows even bigger, blocking current. This is called reverse bias. The circuit is off. This simple on-off behavior is what makes diodes, transistors, and even microchips possible. Real-world applications, where PN junctions rule. You might not see PN junctions, but they're everywhere. In diodes, they let current flow in one direction only. In transistors, they amplify and switch signals, making your computer work. In solar cells, they convert sunlight into electricity. This tiny junction is the reason technology keeps advancing. And now, you know the real physics behind it. Call to action. So, the next time you use a phone, a laptop, or even turn on a light, remember, the PN junction is silently working behind the scenes. Now, I have a question for you. What do you think is the next big invention using semiconductors? Drop your thoughts in the comments. And if you want to see more videos that break down real physics, hit that subscribe button, because in the world of science, knowledge is power. Subscribe now plus watch next recommendation.